Hello. So until now, for the converter system, we didn't really consider the impedances of transformer. That means we had considered the ideal cases for all the simulations, and we also showed in one of our previous videos the transformer voltage level and shifting adjustments using PLECS. So in this video today I am going to show you how to calculate the proper impedance of different types of transformers. I already have prepared a simulation model in PLECS. Let's open the model and go through each part separately. As usual, I have defined the transformer parameters and relevant calculation using an M file. So the target of this video is to find the correct values of the impedance of transformers, and we will verify it using the fundamental concepts of electrical engineering. I take the same transformer as one of the last transformer videos. That means I consider a transformer of apparent power 10 megavolt amperes. 10% is the short circuit impedance for our consideration, and then since we are not particularly interested in a specific type of transformer, I assume that the ratio of resistive to reactive part is 10%, that is 0.1, and I define the high voltage and low voltage sides as 20 and 3 kilovolts respectively. The grid that I consider is 50 Hertz grid. Now for the definition of the turns ratio, it's as usual the ratio of the high voltage to the low voltage side. So let's go from the top to bottom. So on the top we have a source here. Now the idea is to set the voltage level to the short circuit impedance value, so that we can find the corresponding short circuit current on the secondary side. So the idea is, from the definition of short circuit impedance, if we apply the short circuit impedance or corresponding short circuit voltage on the primary side of the transformer and then short circuit the secondary terminals, if the impedances are correct, we should get the rated value of the current on the secondary side. So based on this principle, we will see all the different types of transformers that are implementable in PLECS, and if our results have to be correct, then we need to specify the impedances correctly. So this is the target of this video. Now for all the two winding transformers that we have here, I take a general requirements, all of them. So here I specify for all two winding transformers we have the calculations of impedances. It's the same for all of them, and there is one 3 winding transformer at the top. We will show you later how to calculate the impedances. To start with, I first show the rated current, which is simply the S divided by square root of 3 times the voltage. Now I take the voltage on the low voltage side because, as I said, we will short circuit the secondary side, that is the low voltage side, and calculate the current. So as a source, as a definition, so if we consider only this part, that means a VHV, which is 20 kilovolts, and since this is the amplitude and single phase, we need to add a factor of square root of 2 by 3, and since UK, this is the short circuit impedance value, that means instead of putting the nominal value of the voltage, we put the percentage of the short circuit impedance as the voltage source on the primary side, high voltage side in this case, and after short circuiting we measure the current on the secondary side. So if the impedances are correct, we should get the rated values of the current. So the simple formula here, implementation of impedance calculation for two winding transformers, which is first the impedance, which is UK, which is short circuit impedance, times V square by ST. And then since we considered the Rx ratio, we can find the reactance using this formula. And using this relationship, we can find the resistive part, and the inductance is calculated using this relationship. So if you go to the first transformer, which is a vector group, is star-star connections, actually, the configuration. If we go inside it, we see in the specifications of leakage inductance L1 and L2. So L1 is the primary side and L2 is the secondary side inductance. Similar for the resistive parts. If you see carefully in the number of turns, we have specified the winding ratio. So you can watch the previous video how to specify these winding ratios to step up or step down the relevant voltages, which I defined at the end of the script here for different types of winding ratios and transformers. So the first transformer, this is this one, and so forth. So I will leave this discussion of winding ratio and concentrate on the impedance calculation rather. So as I mentioned, for all three winding transformer, there are a couple of options we can consider here. Like the calculated L or inductance, we can specify the whole part on the primary side. In that case, we need to leave the secondary part to be 0 because the whole inductance is considered on the primary side. Same for the resistor part as well. If we do so, let me run the simulation using the script. For that, we have the command here, simulate or sim, and the name of the model in Simulink. So if we run it, so I have prepared already 2 probes. One measures the voltage of the primary side and the second measures the current of the secondary side. It's true for all other remaining configurations as well. If we open it, the scope, so first one is the high voltage side voltage. If you remember, we had a short circuit impedance of 10%. That means if we measure, if for example we take cursors, take one period 0.02 and we measure at a steady state value. So we had considered the high voltage side to be 20 kilovolts and 10% of that is 2 kilovolts. So the setting is correct for the voltage level. And as we mentioned, if the impedance is calculated correctly, we should get the rated current on the secondary side when we short circuit it. And that is 1.92 kiloamperes on the secondary side. If you remember, we also calculated using the script the rated current to be this. Now let's check if the value of IR is then 1.92 kiloamperes as shown by the graphs. So I will just try, let's try it here. So IR, if we check, the value is now 1.9245 kiloamperes, and if from our graphs it was exactly this value, 1.924 amperes, kiloamperes. That means if we have the correct value of the impedance, then we get the correct value of the current on the secondary side. Now from the same configuration, there is another option. For example, we have another option to specify 0 impedance on the primary side and then transfer the whole of the impedance to the secondary side. In that case, we have to use the factor of U square. So we divide the L calculated on the high voltage side, referred to the secondary side using the factor of U square. That's the turns ratio square. Same for the resistance. This also applies if, for example, we want to divide the impedances on primary and secondary side using a ratio, 50-50 ratio. This transformation is still valid. So for this, the second simulation, we can check if the values are still correct. For this, we take a delta, specify a period, 20 milliseconds, somewhere here, and we are interested in the effective value here. So the first one is the voltage. 10% of 20 kilovolts is 2 kilovolts, and we have the rated current on 1.924 again, which validates the calculation. Now we had the star-star connections in both of the cases. Now things get a little interesting here if we have another vector grouping on primary and secondary side, like this case here. You see we have the star on the primary side and delta on the secondary side. In this case, we need to consider the vector connections as well. That means if we refer the impedances only to the primary side, which is the star side, we don't need to include any factor. We just leave the secondary impedances to be 0 and check the values first. So we take 2 cursors again. I did need to do it every time. So take a period, 0.02 seconds, and I need to specify the RMS. Again, 2 kilovolts and 1.924 kiloamperes. So for example, we now take the whole of the impedance to the secondary side. So you see, first the primary side is specified as 0, and secondary side we need to step it down by the factor of turns ratio squared, if here. And since the secondary side is now delta connected, we need to include the factor of 3, and then we get the correct value. Let's check it here as well. I'll take the cursors. Once we need the delta and another we need the RMS. As delta is 0.02, and we have the relevant values of 2 kilovolts again and 1.924 kiloamperes current. So until now we considered these 4 scenarios. The same happens, we have instead of star delta, and it's similar to delta star. That means, you see, if I specify on the delta side the whole of the impedance, we need to include the factor of 3, and if we calculate it on the secondary side, which is the star side, we don't need the factor of 3. We just step it down using the turns ratio squared. So if we check these 2 values again, it should be exactly the same as we calculated before. So I take the delta for 2 cursors, and I calculate then the RMS, which is exactly the same again. And for the second one, it should be the same. So the 2 cursors, I'll take delta and RMS. So delta 0.02, and again you see the values are same. So this verifies the calculation of impedances properly. Now the principle is same for delta Z on delta Z zigzag transformer. It's the same. I will leave it, you can try it yourself. Interesting part would be then if we have a 3-winding transformer. Now it's a little tricky at this point to calculate the star equivalent impedances of this 3-winding transformer. In that case we need to go to a couple of steps. Say for example we have 3-winding transformer named as primary, secondary and tertiary. So in the intermediary step, we can calculate the impedance between primary and secondary, primary and tertiary, and secondary and tertiary, which results in this delta equivalent. And from this delta equivalent of impedance diagram, we can find the corresponding star equivalent impedances. The relevant calculation formulas are given here. So if we need to, for instance, calculate the primary side impedance, it's half of the ZPS plus ZPT minus ZST. Now Z prime ST is, there is a prime because it is then referred to a specific side. In this case, it is on the primary side. So the reference is important. So it is Z primary PS and ZPT, they are both referred to the primary side. We'll see how to do it with the three-winding transformer in PLECS as well. So for the three-winding transformer, we still consider the power of the transformer to be the same as. And another important point that I need to mention here is that if we consider primary and secondary, you see the flow of the power is not exactly equal to the whole transformer power. In many instances, in real applications, it should be specified. Maybe it's 1/3 of the power, depending on voltage levels on the secondary and tertiary sides. Could be the 50-50 division of the power. For our case, I consider that the power flow between primary and secondary and primary to tertiary is half of the total transformer power. That means for the calculation of the impedances, I need to consider, instead of ST, half of ST. So this is what I'm doing here. So there is a note as well. I can read for three-winding transformer. Let's read it. So for three-winding transformer with the same ST, that's the power, UK, the short circuit impedance, and voltage levels as two-winding transformers. Calculated values for ZPS, ZPT, and ZST from rated values give the delta equivalent for three-winding transformer. So let's continue. So here in the script, you can notice that the implementation of the formulas that I showed you in the presentation. So first, for the ZPS, these three are the delta equivalent of the equivalent circuits. That means these three impedances. And then similarly for the reactance and resistances. Once we have the reactances and resistances of delta equivalent circuits, we can now go to the impedance and then resistance of individual star connection equivalent. You see, this is half of this. It is the implementation of the formula only. Another important point here, since we will be specifying, let me show you here. Since we'll be specifying the impedances already in the dialog box, I can take not the values specified on a specific side, but on the respective sides. This is what I mean. If I calculate the primary side impedance, LP, the inductance in that case, it is referred to the primary side. If we take the secondary side inductance, it is now referred to the secondary side. So you see the first calculated value of impedance, which was on the high voltage side, primary in this case, is now referred to its own secondary side, that is divided by U squared. Same applies for the tertiary side. Once we have these LP, LS, and LT, I can specify to the respective side. The first one for the primary, second one for the secondary, and third one for the tertiary. Another important point to note here is that if the secondary side, in my case, is then delta connected, for this we need to include a factor of 3 in the secondary side. So primary was star, there is no factor. secondary is delta as a factor of 3, tertiary is again star, there is no factor of 3, and these are just the turns ratio, and I want to step the voltages down, so I take the inverse of the turns ratio. And phase legs is 30. This is just as usual values you can take. And to verify if we apply the percentage of voltage on the primary side and short circuit on the secondary side or tertiary side, it's important to note that according to the IEC standard, one of the secondary sides of three-winding transformer has to be short circuited and the other has to be remained open. So this is the condition. We cannot short circuit both of the secondary sides or leave both secondary sides open in order to verify or validate our calculations. So as you see, we have applied the percentage of the voltage to the primary side, short circuited the delta secondary side, and open circuited the tertiary star connected side. If this is the true, then we'll again measure. So here I will measure on the primary side. The first one is the voltage, secondary is voltage is 0 because it's short circuited, and the current is then this. I need to check this here. Current is here, secondary one. So if we take a period like delta is 20 milliseconds, if we check the values, you see we have 2 kilovolts, which is correct, and 961 is the rated current. Let's check if this is the case. So to calculate the rated current of the secondary, this is how we calculate it. If you remember, the power is divided, so this is S divided 2 divided by square root of 3 times the voltage. So IRS, the secondary side rated current, and IRT is the tertiary side secondary current. And if we check the values of the rated current of the secondary side, which is 962.25 amperes, this is what we see here as well. You see the secondary current, which is the second curve here, is 961.63, so almost the same. That means now we can do for the star connections as well. So in that case, we will open this delta connections and short circuit the tertiary side connections. Let's run the simulation again and check the values. In that case, the third is the current here, third one. Yeah, and you see the 961.6 or 962 almost is the value of the current. Now why it is so important here, we will see in our coming videos that the design of real-world converter systems, the calculation as shown here of the transformers is extremely important, because the performance of the converters, the power electronic converters, are hugely dependent on the upstream inductance, mostly coming from transformers or chokes. So I think this series of videos, these are one of the fundamental simulation skills that will help us to build even complex converter systems in coming videos. Stay tuned and let me know if you need more information about the videos and tutorial series. I'll try my level best to help you. Thank you very much.